Here are a few examples of tooling that we use to make carbon parts. So this is, for example, the pattern, the positive mold for the dashboard of the C2 that we saw being designed in the tool development. And so this is a positive, that's not the actual tool. Out of this, we make the carbon fiber negative because it's a big and complex part. Sometimes we make a direct mold, like for example here, this is the mold for the C2 mirror. And that's a multiple piece part because you have undercuts, so you wouldn't be able to take the part out after curing if the mold was not disassemblable. So when you have a part like this, when you have a mold like this, the part is made directly in the mold, like for example this part. But for more complex shapes, we usually have this step in between where you first have to make a positive and then a carbon fiber tool. And this is actually great because the tool has the exact same expansion rate like the part, because carbon fiber and aluminum in the oven, in the autoclave, when it gets hot, they don't expand exactly the same. So you have to calculate in how much it deforms during the curing. So when you have a carbon fiber mold, you don't have that problem. So let's see how we make parts based on these tools. This is where we laminate all the parts, and we use a bunch of different materials here. So let's take the simplest one. This is raw carbon fiber. So this doesn't have any resin inside, it's dry. This is pre-preg carbon fiber, which means it's pre-impregnated with resin. So we have to keep those in big fridges because the resin starts to react on temperature. And we have a bunch of different pre-preg materials that are bigger like these, bigger weaves or smaller weaves, depending on the application and what we want to do with that part. But also different other materials, like for example Kevlar or glass fiber for electrical insulation and copper for EMC shielding. So for example, what you need to do in some cases, for the exterior parts of the car, for example, you use exclusively carbon fiber only. But for some components, like let's say a PDU housing, power distribution housing, which is an electrical component, you need to have electrical insulation. So you cannot use carbon fiber because it's conducting electricity. So you use glass fiber sheets with copper laminated into them for electromagnetic shielding. And then sometimes you want to use Kevlar for penetration protection if, for example, you have some kind of crash or you pick up a part from the road and it can penetrate in the battery pack. That's why we use a different mix of materials, and it's very important how these materials are laid. So we make here the obvious components, which are like the doors or the bonnets or the interior parts, but also some technical components like battery pack housings or module housings or power distribution housings and so on. So it basically starts with a roll of material. It starts with the roll of carbon fiber or glass fiber or whatever you use for that component. The machine is cutting those rolls and the laminators get the cuts and then laminate them in the order that they get from the ply books. So we have the ply books which says which part or which material has to be laminated when, in which order, in which direction. And this is really important to follow this because, for example, sometimes we use unidirectional carbon fiber, which means it can pick up force only in one direction. So if you have a wrong angle, if you have a misalignment there, then the part is not structurally sound because it cannot pick up the loads for what it was designed for. After lamination, the parts are vacuum bagged. For example here, these parts are put in a vacuum bag. So it's important to suck all the air out from here because in the autoclave it's all being pressurized. So to have a fitting of the carbon fiber plies to the tools. So after this station, they go into the autoclaves. And then there we put them under immense pressure and temperatures to cook them basically and make the resin react so that the carbon fiber plies from a soft textile-like material become harder than steel but lighter than steel. After this process, they get put out of the mold, get trimmed, cut, bonded, if necessary, upholstered, or in some cases painted. So after this process, we take it out, cut them on the other side of the facility, and then it comes here into our paint shop. So the paint shop is right next door to the carbon fiber production. So when we have some parts that are difficult to make, the guys can work with each other to figure it out. So what's quite difficult to do is to get the perfect carbon fiber weave surface finish. So we have worked years on that to get that really right, and especially with complex shapes like this. So we can see some Concept 1 parts being painted here, and these are basically for the last two Concept 1s. We also have some C2 parts being in painting now, and after these two C1s, we are completely switching to the C2. We are now in our battery assembly area. So here we have, for example, a Seat battery pack, or here is the production line for the Koenigsegg battery system. We can see one of those batteries here. So that's a very unique battery pack. It's the most power-dense battery pack in the industry. So if you look at C-rate, for example, a normal electric car will have like 1 or 2 or 3 C discharge. So it means if it has 1 kilowatt hour of energy, if it has 1 C, it can discharge with 1 kilowatt. A Tesla battery has 5 or 6 C discharge capacity. This battery has 120 C discharge capacity. So it's on a completely different level. Of course, it's worse in terms of energy density, but better in power density. So that's the kind of stuff we are quite good at. So if you look at the 5 hybrid electric hypercars coming to the market, so the Koenigsegg Regera, Aston Martin Valkyrie, the Pininfarina Battista, Rimac C2, and Mercedes Project One, out of those 5 cars, 4 have our batteries and other parts. So we are quite proud of that. And it all starts basically with battery cells. That's the only part we don't make on our own. So we have a few examples here. So this is a cylindrical cell with aluminum housing. This is another cylindrical cell, the so-called 21700 format, which is the new format where most of the industry is switching to. And these are the older format cells, 18650. So the difference is basically in the size. The chemistry is very different depending on the application. It can be lithium oxide or NMC, NCA, or this one is lithium polymer pouch cell, so it's a very different cell. So depending on the application, there is never like a perfect battery cell that fits all. It always depends on what you need to achieve with the project and with the battery. And just to give you a feeling how important the cell is, so in the Aston Martin battery pack, for example, we have 3000 parts, and out of those 3000, only 400 are the cells. So there's lots of things you have to do around the cell to make it a working battery in terms of cooling, battery management system, structural integrity, safety, to get the performance out. So we consider the cell a building brick out of which we build the house. We cannot go too much into the details what we do here, because some of the things we do is confidential for other car manufacturers. So we have lots of projects going on that are not public yet, so I cannot show you everything, but just to give you a glimpse of our battery production. And here's testing. This is where we are testing our batteries and powertrains. So let me show you our motor dyno. So this is a little bit of a mess, but if you go out and try to buy a 600 kilowatt dyno, it's millions of euros. We didn't have that money to spend, so we developed our own and built our own dyno system, which does what we need to do. So basically what we have here is a Concept 1 rear axle. So these are 2 motors connected together. So this is 660 kilowatts as a load and 880 newton meters of torque. And here we have the new C2 rear motor being tested. So what we wanted to achieve is in the same package of one motor of the Concept 1 to have much more power. So instead of 300 kilowatts here per motor, we have 500 here. And instead of 400 newton meters, we have 700 newton meters. So we are using those 2 motors as a load to test this one. And another change we have, so here in this motor in the Concept 1 we had the oil sump in the floor. So it's oil cooled, and then you need to have a heat exchanger from the oil to the water. So you need 2 pumps, heat exchangers and so on. So what we wanted to achieve with the new motor is to have only water cooling, to avoid having multiple cooling systems and multiple pumps. This is just showing how we do things. We try to be very cost efficient and do things on our own to save money. That's why we managed to do what we are doing, because we are very cautious always. One of the biggest issues we have with the space is testing. We need lots of more testing facilities. So we have to use other people's facilities at the moment to test batteries and so on, just because we don't have space. We even build containers outside to build test equipment for testing the batteries and so on. So just let me show you how it looks like when we test some battery packs. When we test the battery, we hook it up here. So all the high voltage, low voltage and cooling systems are connected just as they would be in the car. We have drive cycles. So for example, the battery being tested here right now, it feels for the battery exactly as it was on the Nürburgring. So it gets exactly the load, the charge and discharge cycle, as you would get in the car. So for the battery, there is no difference between being tested here or in the real car, except vibration, which we don't have. In this test station, we have that outside. So this is perfect to test how a battery would behave. So first you do simulations, then you do cell level tests, module level tests, and then the whole battery pack being tested in this way based on the data you have from the track cycles. So we saw the last Concept 1 chassis there in wiring. After the wiring is done, the chassis come here and they are being assembled to the final car. So this is nest production, where the chassis comes here and all the parts are being built into it while the chassis is stationary, it doesn't move. So it's not an assembly line. The C2 will be produced in an assembly line in a new location, but for now we do it here, like that. So these, the other chassis together with these two are the last 3 Concept 1s. Which we are now finishing and then shifting the production completely to the C2. But in the meantime, we already have C2 prototypes in production, which we can see here. Here we have the C2 monocoque. We are at the same time building the last Concept 1s and building the C2 prototypes. So they are being assembled now. We want to make 30 prototypes, which will be produced before the first customer units are shipped, for testing and crash tests and homologation. Unfortunately, a bunch of these will end up in walls and in poles and crash tests and all of that stuff, so we'll have to crash many of them. What's interesting here is that this is the biggest carbon fiber piece in industry. So we can see, for example, the front suspension and the rear suspension are actually on the same part. So the monocoque goes all the way from here, from the front crash structure to the rear crash structure. So it's 80,000 Newton meters per degree torsional rigidity. So just the monocoque without the roof, which is a bonded part, just the monocoque has 2,200 carbon fiber plies and 222 aluminum inserts. It has a fully integrated structural battery pack and the front and rear powertrain, which we saw in the powertrain assembly. So the powertrain for the front, it's in here, so it's inside the monocoque, and the rear powertrain is also inside the monocoque protected. Here's where the rear powertrain sits. Here comes the inverter, the motors and gearboxes. Here's a bunch of electronics, and then under it here, and in the tunnel, and under the feet of the passenger and the driver is the battery pack. Then here comes the rear crash structure, and as you can see here, the rear suspension is on the same part like the front suspension, so it's one single huge piece. Very complex and very difficult to produce, but it gives a lot of advantages in terms of rigidity, safety, and performance. Our engineering is divided in 2 large groups. From one side we have the vehicle engineering, which is developed in the car, and the component engineering.
Here we have some design directions for our newest C2, for the HMI, for the graphics that you will see on the displays.